Here we are tasked with finding the thermal conductivity of some sample heated at steady state by a resistance heater. We know the physical dimensions of this sample as well as the power provided there at that steady state. So we can use heat conductivity and substitute some terms for dt dx. We can use the difference in temperature as well as the width of that sample. Then we can rearrange for the thermal conductivity K, assuming again steady state and that these upper and lower insulators have negligible heat loss. And then we can solve for that thermal conductivity K. Here there is steam in a pipe where we are Here there is steam in the pipe and we're trying to find the heat loss and the energy cost from that heat loss. We're just going to use Newton's law of cooling and substitute in what we know about the system, the temperatures and the physical dimensions, using the surface area of the cylinder, specifically just the outside of the cylinder here. And then we can solve for that heat loss in BTUs per hour. To find the energy cost, we know steam is generated at 86% efficiency and we have the price here. So we can find the amount of heat loss per year. We can use the efficiency to find the required heat and then use that price to find how much it's going to cost per year. Here we're trying to find the temperature at the surface of a spacecraft when the emitted energy is equivalent to the absorbed energy. So we're going to use Boltzmann's law and also Kirchhoff's law, set the Q emitted and the absorbed equal to each other using our givens. And then we can find the temperature of the surface by rearranging based on a steady state constant there, and then that the emissivity and absorptivity we were given are constant across this whole surface. Here we're simply asked to find the driving force for heat conduction and mass diffusion, which are the same form of equations. So we've got this rate of heat conduction, rate of mass diffusion, thermal conductivity, and then for mass it's mass diffusivity. Area is in both cases the area normal to transfer, and then dt dx is a temperature gradient and a concentration gradient respectively. Finally, we need to find the diffusivity of CO2 in air, so we can use a ratio of the diffusivities based on a known value from tables in the book. We can use the known value as our state 2 and state 1 be the given conditions, and then solve in each case for the diffusivity. My only point of confusion on this homework might be that I had some deviation from the solution for this final one, and I think I see why. I think that's from their different method used, where they used a point closer to the actual conditions based on table 14.1, where the temperature was actually the same and only the pressure differed. So because these are experimental, that results in a less deviation. But I would just be curious how much that differs over different methods, because I just used a fixed point given in table 14.2. And then finally, my only last point of confusion is maybe I didn't fully understand how thermal symmetry worked for this problem 1, which was something called out in the solution. It resulted in a lower k. I was not able to figure that out within the time, so that would be my only final point of confusion.